Direct adaptive control of manipulators, an introduction. This will be the topic on which we will be discussing today. We discussed various control systems while discussing various aspects of neural control, but next couple of lectures or next series of from today onwards, the series of lectures that we will be delivering, they will be unidirectional, means the focus would be application to manipulators, and we have already discussed what is direct adaptive control earlier. Now, this direct adaptive control of manipulators, this will be specific, that means this physical system is fixed. So, how do we design control schemes for manipulators? That is what. So, we will go step by step. Today is the notion of direct adaptive control for manipulators that would lead to a neural network based direct adaptive control, and then we will continue the backstepping and singular perturbation based neural network control. So, topics that will be covered is manipulator dynamics, direct adaptive control scheme, computer torque control, adaptive control, robust control, neuroadaptive control, and summary. Manipulator dynamics, we have already been talking about this dynamics for a long time. So, the usual dynamic is m q q double dot v m q dot f q dot g q plus tau d is tau. So, in this the inertia matrix m q, this one is symmetric, positive definite and bounded. This is a property for all rigid link manipulator, this property is satisfied. So, that mu q m q, the inertial matrix, can be written as less than mu 2 I and greater than mu 1 I for all q t. Q, you know, the q is angular position, q dot is angular velocity, q double dot is angular acceleration. The second is Coriolis centripetal vector V m is quadratic in q dot. V m is bounded, so that we can write V m q dot norm is less than V v norm q dot whole square. So, here this V m q dot is this total quantity. The Coriolis centripetal matrix can always be selected, so that matrix S q q dot is m dot q minus 2 V m q q dot is q symmetric. Q symmetric means if a matrix is a q symmetric, if S is a q symmetric matrix, then this condition is satisfied, x transpose S x is 0. And in this case, if we compute what is m dot minus 2 V m, this quantity, and we multiply any thing here is 0. This is called skew schematic property. The friction term is bounded. This is the friction term, f q dot is friction term, is bounded by this quantity f b. F is b some constant q dot plus k b. The gravity factor is bounded, so that g q norm is less than or equal to g b. The disturbances, the tau d, this is a disturbance torque, and this is the actual torque actuated at every joint. Okay. So, disturbances are bounded so that this norm is less than dV. It is often convenient to write the robot dynamics as mq double dot plus nq dot plus tau d equal to tau. For practical purpose, we will just not consider disturbance to occur for the moment during the analysis. Of course, for in the simulation we will use the tau d, but in the analysis we will just remove tau d. So, in practical purpose, mq double dot plus n equal to tau, where n is Coriolis forces plus frictional the force due to friction and the force due to gravity. So, they represent a vector of nonlinear terms. It is assumed that tau d is 0. Reconsider now the robot dynamics, which we said mq double dot is nq equal to tau, where this n consists of Coriolis forces, gravitational forces and forces due to friction. Now, let us define the state space x as the vector consisting of position, angular position vector and angular velocity vector. So, we can rewrite robot dynamics as in the state space form. This is one state space form. In state space model, you can easily see x dot is q dot, right. That is, you can write here q dot q double dot, the vector. So, x dot is q dot q double dot. So, the q dot part I can put a line here. So, on the top line q dot 0, that is always true. The second part is q double dot. You see the q double dot is this one, which is obviously minus nq into m inverse. So, m inverse minus nq, which is this one, and plus m inverse into tau. Okay. That is very straightforward. And there is another state space model. This is the model 2. In this model, the Brunowski canonical form, the same robot dynamics can be written as q double dot minus m inverse n plus m inverse tau equal to u. So, this quantity, if I say u simply, okay, then this is my input now. So, how do I write q double dot? Q double dot is sorry, x is q dot q double dot, okay, equal to u. So, q double dot equal to u, you see that if I put this line here, q double dot is simply u, which is q double dot is u, and q dot is simply, so this is x is again q and q double dot, sorry, q and q dot, q dot. So, obviously 0 q dot is, you can easily see 0 q is 0 and I q dot is q dot. Okay. So, q dot is this and 0 and the top one is 0, u is 0. So, q dot is q dot and q double dot is u, right. So, simple by partitioning I can explain that this is and where u is this quantity. This is a virtual control u. This is the second model. So, direct adaptive control schemes. In direct adaptive control, the control parameters are directly adjusted to reduce some norm of output error. It does not require explicit system identification. So, we do not do explicit system identification in direct adaptive control. That what is the system model parameters exactly in the sense of system identification we do not do. So, we will first talk about computed control, which is a non-adaptive control, an exact control. We assume that all the parameters of the robot manipulators are known. Then what is meaning of computed control? We will go from that when assuming relaxing the condition that some of the parameters are unknown. Then we go to adaptive control. I will not really focus on a robust control because that is not our topic today, but I will just give you a little idea about what is robust control, and then I will from adaptive control we will go to neuroadaptive control. Okay, and the difference between these two we will try to understand today in this class. So, computed control, it uses feedback linearization technique. Define the tracking error ET is the desired trajectory minus the actual trajectory. Differentiating twice this quantity, we get E double dot is QD double dot minus Q double dot is QD double dot minus M inverse tau. So, QD double dot and Q double dot is you know that Q double dot is already M Q double dot plus N is tau. So, Q double dot is minus M inverse So, writing properly here we can write, we know that the robot dynamics M Q double dot plus N is tau. This is our simplified form, and so I can write Q double dot as minus M inverse N plus M inverse tau. So, if I take this quantity and put it here instead of this, Q double dot is placed here. So, you get Q D double dot M inverse N minus tau. By choosing the state vector x is u e t e double dot t, we obtained the canonical form like this: d by dt e dot is 0 I 0 0 x 0 I u. So, this is the state closed error dynamics. This is normally we say closed loop error dynamics, where the control action u t is q d double dot plus m inverse q n q q dot minus tau. So, this is virtual control action, but from here we can easily see the tau can be computed from this. You can see that this is so ut is defined as this one. So, where the tau is computed, what we have to see is that now the objective would be what should be the u for which the system is stable. You take that u and put it here and then find out what is tau. This is the reverse process. Okay. Now, choose u to stabilize the error dynamics, then compute the required arm torque as tau is m q q d double dot minus u n q q dot. So, if I write now here tau I want to compute, then I take q d double dot minus u this side, and this side if I take the other side. So, m inverse q and q q minus tau to go. So, from there you find out n tau is mq qd double dot minus u plus nq dot. Now, what is this u? So, if I want to stabilize this particular system using a PD controller, then my u is simply u is minus kV E dot minus kPe. Okay. So, this is called PD controller, okay, where my E is QD minus QT. So, this will stabilize the system. So, by plugging these values here, I get tau is mq qd double dot plus kve dot plus kpe, this one, plus nq dot is vm q dot fq dot plus gq. But this control action I can actuate provided all the parameters, that is m, vm, f, g, all are known. The parameter that I have to only design is kV and kp. Similarly, PID, computer torque control, would be, I just create another one for PID, epsilon dot is E, right, that is epsilon is E dt integral. Then your torque is, this is my minus u. So, mq is, this is minus u. So, u is minus kV dot minus kP plus a minus ki epsilon. Okay. So, this is the integral term, because epsilon is E dt. So, this implies epsilon is, so this is the integral action, this is the proportional action and this is the derivative action. So, this is the PID controller. So, the PID computer torque control is given by this function. Now, let us take a simple example, a q double dot b sin q is tau, which is a single link manipulator, a is ml square, b is mgl. Now, if I differentiate tracking error E, you get a e dot double dot is a q d dot minus a q dot, which is a q d double dot remains, and a q dot is b sin q minus a q dot is b sin q minus tau, so which is f q minus tau. So, the computer torque control tau is obviously f q plus, this is my the u term k d dot plus k p e, yields the following closed loop aerodynamics, a e double dot k d dot plus k p equal to 0, which is stable and achieves trajectory tracking. So, this is my closed loop aerodynamics. Okay. So, the just like here we said that you select u, put it here, this u, then this becomes closed loop aerodynamics. So, that putting this u as a PD controller for a single link manipulator, the dynamics is a stable dynamics. Now, the computer torque control, if I take a two link manipulator, link 1 and link 2, actually this is actually can be written as in the usual form mq q dot double dot vq q dot. So, in this the q dot term, that is, this is actually vm q dot is multiplied with v, together is the total Coriolis force, gravity force equal to torque, where if I define alpha as this quantity, where a1 is the link length 1 and a2 is the link length 2, q1 is the angle of link length 1 with the horizontal axis, and q2 is the link angle of link 2 with the along aligned with the link link 1. So then if I define alpha, beta, eta as well as E1 as this particular manner, the dynamics can be written in this form. So this is your M matrix, this is your V matrix, V is a Coriolis force, and this is your gravity force. This quantity is tau 1, tau 2. So tau 1 is actuated here and tau 2 is actuated here. So you say that if you do the simulation, if you give some small disturbance, then you see that the PD controller has some error, some steady state error, it does not exactly go to 0, whereas a PID controller, even if any disturbance, it goes to 0. So that is, the steady state error is eliminated in case of PID controller. In case of PD controller, it is not eliminated, which is expected. So now computed torque control, computed torque control works very well when all dynamical parameters MQ, VQ, FM, F, G are accurately known. In case of robot manipulator, these parameters are not properly known or vary with time. The control objective is to achieve trajectory tracking under parametric uncertainties. So two approaches that are normally followed is adaptive control and robust control. So what is adaptive control? So I will first introduce what is filtered error approximation based control. The filtered tracking error defined as is R, this is the filtered tracking error, which is E dot, the derivative of the error, plus lambda error. So lambda is a matrix, R is a vector, E is error. So E is QD minus Q, you know that Q is a vector. So if I have a 2 link manipulator, Q dimension is 2, if I have n link manipulator, dimension of Q is n. So the error is a vector, so R is also vector. So this is a matrix obviously. So if E is 2 dimensional, the matrix is 2 by 2, E is n dimensional, matrix n by n. So taking Laplace transform for a scalar case, if it is a scalar thing, then we can write out Es is Rs upon S plus lambda. So the tracking error can be obtained by passing the quantity R through a low pass filter. You can easily see this is a low pass filter, hence the name, which is that filtered error tracking. This kind of error representation leads to a simplified controller design owing to reduction of the system order. Boundedness of R ensures boundedness of E and E dot. So this is just certain ideas that if I know that R is bounded, which is R is E dot as we saw, lambda E, if R is bounded, this is bounded, then it ensures that E is bounded as well as E dot is bounded. Okay. So that boundedness is defined by this, E bounded is less than R bounded by sigma m, this quantity, and the boundedness of E dot is less than boundedness of R. The desired trajectory is bounded, so that QD, QD dot, QD double dot, this is less than QB. So always also we define a boundedness of the desired trajectory. The robot dynamics can be expressed in terms of filtered error. So once I define R as E dot plus lambda E, given that the robot dynamics is what? M Q double dot plus n is tau. So this can be written as M R dot equal to minus V M R plus F x minus tau, where the nonlinear robot function is defined as f x is m q q d double dot plus lambda e dot plus b m q q dot q d dot plus lambda e plus f q dot plus g q. Okay. So, we can derive this equation if I define R and given the robot dynamics. So, this is the error dynamics, filtered error dynamics, where this x here f x is E transpose E dot transpose q d transpose q d dot transpose q d double dot transpose transpose. So, you see that this state vector x is all known quantities, because I know from the robot dynamic movement motion of the robot, I know what is the position and what is velocity. So, I know what is E and E dot, and desired trajectories are already given. So, x is known actually. So, this quantity is actually known quantity of x. This is not an unknown quantities, provided all these quantities m q, v m, f and g are known. So, f x contains all the potentially unknown robot parameters, arm parameters. That is how we have separated that in this f x we have all these parameters, unknown parameter m, v m, f and g. So, the approximation based controller. So, previous one was m r dot is minus v m r plus f x minus tau. So, in that tau is f hat plus k v r minus v t, where f hat is an estimate of f x, k v r is an outer p d tracking loop and v t is robustifying term. So, if I assume this my controller control action, okay, and replace this action in my term which is m q double dot n equal to tau. So, if I put this tau here, that is in this tau f hat plus k v r minus v t, then we eventually reach this closed loop error dynamics, which is m r dot minus v m r minus k v r plus f tilde plus v t, where the function approximation error f tilde is f minus f hat. The controller design problem is to select the estimate f hat and this v t in the above approximation based controller, so that the closed loop error dynamics is stable. So, adaptive control can be applied to a class of nonlinear systems that satisfy following condition. The nonlinear plant dynamics can be linearly parameterized, the full state is measurable, nonlinearities can be cancelled stably, that is without unstable hidden modes, by the control input if the parameters are unknown. Robot manipulators usually satisfy these conditions. So, adaptive control of robot manipulators, rewriting the robot dynamics in terms of filtered error, which is m r dot is minus v m r plus f x minus tau. So, this is the actual robot dynamics in terms of filtered error, where the nonlinear function f x may be expressed as a linear function of unknown parameter as shown below. So, this we have already shown this f x, and this can be written. Now, if I can approximate this as in terms of, because I can write this equation in terms of a regression matrix and an unknown parameter vector phi. Okay. So, this is very important. I can show you what does it mean, this w x and phi. You see that if I write a single link manipulator which is a q double dot plus v sin q is tau, okay, is tau, right. So, this particular thing can be written in Wx phi as you see that q double dot sin q. This is my regression matrix and this is my parameters a and b is tau. Okay. So, this is the meaning of Wx and phi. So, this Fx which we are talking about, this is a nonlinear function. This in case of robot manipulator can be represented in terms of a regression matrix Wx, and these are all known quantities provided if we, because q dot, and normally it is okay, in this Wx q double dot will not be there. It is not in this example, it is q double dot, but normally this all quantities, this regression matrix would have all the quantities, those are all measurable state vectors and we can compute that. Okay. So, where Wx is known as a regression matrix and phi is the vector of unknown parameter, and in this case unknown parameters are a and b. So, one adaptive controller which is Slotin designed in 1988 is that the control action tau is given by Wx phi hat, the estimated parameter, plus kVr, very simple. This is kind of a PD kind of controller and this is our regression matrix into phi hat. Okay. So, this is exactly, this quantity is exactly f hat x plus kVr. Okay. So, you can easily see that if I do that here, tau is exactly fx plus kVr, then this system is stable, this system is stable. But when it is f hat, then the system stability is for you have to again have a law for phi hat, because we do not know what is phi. So, phi hat dot is gamma, which is a positive definite matrix, W transpose x into R. So, this is the parameter update law. So, phi hat dot, this is parameter update law. And this is control law. So, you will find always adaptive control means we will have a control law, and in this control law consists of a term called unknown parameter phi hat, and that unknown parameter is computed using parameter update law, which is phi hat dot is gamma W transpose x R. Okay. The estimate of nonlinear function is given by f hat x is Wx phi hat due to linearization property. So, this is linearization property, as I told you earlier, that robot dynamics can be written as a regression vector W into phi is tau. This is a robot manipulator. Any robot manipulator can be written in terms of phi is the vector of unknown parameter, W is the regression matrix. So, f tilde is of course Wx phi tilde is phi minus phi hat, the parameter estimation. The above adaptive controller yields following closed loop filter dynamics Mr dot minus Vmr minus Kvr Wx phi tilde. You can easily see now that if I have this quantity, if phi tilde is 0, that means if I know the parameters, then this is a stable dynamics, okay, because M is a positive definite matrix. So, R dot is Vm plus Kvr. Okay. Now, select the Lyapunov function, but the point is that we have this quantity. So, select the Lyapunov function candidate. Actually, whether the system is stable or not, when this quantity is not there, we can do again Lyapunov function analysis to show that this is stable. But now we will take the total thing and we will show that the system is stable by given the parameter adaptive law. So, this is the Lyapunov function, which is R transpose M R plus half phi tilde transpose gamma inverse phi tilde. So, if I take the rate derivative of this Lyapunov function L dot, I get this quantity, okay, R transpose M dot R plus R transpose M R dot, and then phi tilde transpose gamma inverse phi tilde dot. So, this is direct. Now, substituting the error dynamics R dot, and what is error dynamics? That is M R dot is minus V M R minus K V R plus F tilde, which is there, minus V M R minus K V R W x tilde. That is same actually, W x phi tilde. This is same as F tilde. So, if you look at now this this is my R dot. So, if I replace R dot here, so M inverse also comes there, and putting this quantity R dot here, we get L dot is this quantity. So, you know that the robot dynamics has a skew symmetric property, that means M dot minus 2 Vm is skew symmetric, and hence R transpose this quantity into R, this goes to 0 due to skew symmetric, and then L dot is minus R transpose K V R. So, this is negative definite. So, this L dot can be made negative definite if I say this is 0. So, from here I get the parameter update law phi tilde dot is minus equal to minus gamma W transpose X R, and phi tilde dot is minus phi hat dot. Okay. So, that is how we got the so, because of skew symmetric property, this quantity is 0. So, now selecting the parameter update law phi tilde dot, which I said minus phi hat dot is minus gamma W transpose R. So, obviously, my parameter update law was phi hat dot is gamma W transpose R. So, if this is the parameter update law and this is my control, this control action, this is the parameter update law, we proved that the system is Lyapunov stable. So, L dot is negative type. Hence, R and phi tilde are bounded according to Lyapunov's theorem. In order to show that R t tends to 0, t tends to 0, one may use Barwell's lemma to show that L dot goes to 0 with t. So, with that R goes to 0, R goes to 0 means obviously E and E dot goes to 0. Okay. Differentiate Lyapunov function, once again you get L double dot is 2 R transpose K V R dot, substitute the aerodynamics to obtain this quantity. The right hand side is bounded because of the bounding assumption of the manipulator, and demonstrated the boundedness of R and phi tilde. Hence, L double dot is bounded, implying that L dot is uniformly continuous. By Barbolet's lemma, L dot tends to 0 as t tends to infinity, thus R t tends to 0 as t tends to infinity. However, this does not ensure parameter convergence. Okay. So, the adaptive control, direct adaptive control, as we have been saying, that in direct adaptive control, the objective is not to parameter update law will give you the exact parameter, but always the error will goes to 0, the tracking error will go to 0. So, what we finally said that the direct adaptive controller ensures the tracking convergence, direct adaptive control ensures tracking convergence, but not parameter convergence. So, we will take an example of adaptive control. Consider the same second link manipulator that we showed earlier, where the parameters are taken as follows. The desired trajectory was selected as the first desired trajectory for the link 1 as sin t and desired trajectory for the link 2 as cos t. The parameters, the PD parameters, kV is 20, diagonal 20 20 means this is 20 0 0 20, and gamma was actually the parameter update law requires the vector matrix gamma, which is again 10 0 0 10, and there is a filter tracking error which is E dot plus gamma E. So, where gamma is diagonal 5 5. So, the elements of 2 by 2 regression matrix are given as W11 is given this, W12 this quantity, W21 you will find it to be 0, W22 is given by this quantity. You can easily see for a 2 link manipulator this regression matrix is quite involved. So, now if you implement this in simulation, this is actually simulation, not experiment. So, in simulation, if you see, the red was the desired QD1 and blue is the actual Q1. So, you see that in the beginning red and blue they do not match, and but after some time the tracking is perfect, very perfect the tracking. Similarly, the desired trajectory in link 2 is QD2, which is black, this one, and the green is the actual one, this one. So, in the beginning there is lot of discrepancy which is obvious, but as time progressed green and black they converged and there is no tracking error. Okay. So, tracking, this is tracking is perfect or accurate. And now you see that the estimation of mass, which is m1 and m2, these two things we assume they are to be not known. So, if you look at that, the actual mass is 0.8 and 2.3, but here you see they do not 0.8 and 2.3 they really do not converge, and actually they have become same here. So, the estimated quantities are not, they do not converge to the actual quantities, but tracking is perfect. So, that is the objective of adaptive control. So, finally, going back to the discussion on adaptive control. In adaptive control, the primary effort goes into selecting a dynamic estimate f hat for the nonlinear function. Controller have their own dynamics and thus closed loop dynamics are more complex. As a controller is tuned online, the control effort is less as compared to that of robust controllers. Regression matrix Wx must be known accurately for controller to work. Linearization property assumption is restrictive, because this is not this type of controller that we talked about only valid for robot manipulator, because that follows a linearization property. and this linearization property is not valid for all kind of nonlinear system. So, that is why whatever we will be discussing in this following lectures, they are only meant for robot manipulators, because there is a certain advantage, but in general it is not true. So, the computer torque control robot manipulator can be expressed in terms of filter tracking error as fx kVr, where fx is this quantity and adaptive controller is fx hat kVr. So, you see that this is my computer torque control and this is my adaptive control, where fx is replaced by f hat. So, in adaptive control is an approximated computer torque control, where f, the actual f, is replaced by the estimated f, and for that we have a parameter update law, that is given by phi hat dot is gamma w into r, w transpose into r. So, it is seen that adaptive controllers are complex because of additional estimator dynamics. Simpler controllers can be designed if bound on an uncertain nonlinear term f is known. So, in robust control, an additional robust term Vt is added to the computer torque control as follows. So, this is the connection. So, this was our adaptive control law, and then we found out, but here we add a robustifying term minus Vt. So, primary design effort goes into selecting this robust term Vt, so that the system is stable. Okay. So, here this is our controller action, this is my V, and f is an estimate of fx that is not changed on line. Fx is a bound on uncertainties. So, if I know this bound on uncertainties, the intent is that fx is a simplified function that can be computed using bounding property of robot manipulator, even if the exact value of complicated nonlinear function fx is unknown. So, rewrite the robot dynamics in terms of filtered error is this, we have already shown that, and substituting the above proposed controller into this, we get this closed loop error dynamics, and taking the Lyapunov function as half r transpose mqr and differentiating, you get this quantity. Okay. And because of skew symmetric property, this quantity goes to 0. So, now you see that from here we can find out what is V. Okay. So, using the norm property, we get L dot is this quantity and this quantity. So, there are two cases to consider. I am just going a little faster because I have to go to the neural network based controller. So, there are two cases to consider. So, the boundedness R is greater than or equal to epsilon. According to the definition of robust control term Vt, one has L dot is this quantity, which is less than this quantity, this is same, and this is defined, this is replaced by simply R fx. So, you can easily see this cancels out. So, this L dot is only this quantity, which is negative definite. Okay. And case 2, when is less than epsilon, in this case according to definition of robust control term Vt, one has again this quantity, which is this quantity plus R fx 1 minus R bounded upon epsilon. Last term is generally positive, this quantity in this region, and so nothing can be said about whether L is increasing or decreasing. In general, L may be increasing in this region, so that R increases towards epsilon. Okay. So, robust controller example, consider the same two-link manipulator as discussed earlier. The control parameters are selected as with epsilon is 0.1. For a robust PD controller, we take f equal to gq, control input is given as this quantity. So, if you implement, you see that finally given a initial trajectory disturbance, finally it converges to 0. So, position tracking error convergence under robust control action. The primary design effort goes into selecting the robust term V in torque equation. Robust controller do not have dynamics of their own and hence simpler to implement. It is necessary to compute the bounding function effects for uncertainties. More control effort is required as the controller is not tuned online. So, now this is the final part of this lecture. We will be talking about a neural network based adaptive controller. Okay. So, that how we can do the same direct adaptive control using neural network. Take a simple example, a q double dot plus b sin q is tau, which is a single link manipulator. Define as usual, E is q d minus q, E dot is q d dot minus q dot, and the tracking filter tracking error R is E dot plus lambda E. Then we have R dot is q d double dot plus lambda E dot plus b upon a sin q minus tau upon a, okay, which is, this is my regression matrix F, sorry, this is my F this minus u. So, the N can be used to approximate this nonlinear function. This F can be written as w hat phi plus epsilon, and suppose F is w phi. By choosing a controller u is f hat plus kr, the closed loop aerodynamics can be written as R dot is w tilde transpose phi minus kr. So, what I am saying here, that this nonlinear function is represented by a neural network. Okay. So, that is very simple, because w is the parameter, the weights of the neural network, and phi is the input to the neural network. So, the closed loop aerodynamics can be written as R dot is w tilde transpose phi minus kr. So, if I now take a Lyapunov function V in this form, which is R transpose R w tilde transpose gamma inverse w tilde, the time derivative of Lyapunov function is R minus R transpose kr, and then this is trace, the trace of this quantity. So, we can make V dot is minus R transpose kr provided this term is made to 0. So, that can be achieved. W tilde dot is gamma phi R transpose, which you can easily see. So, I can take this comma W tilde transpose, phi R transpose is minus gamma inverse W tilde dot. So, W tilde dot is gamma phi R transpose. So, which is this one. So, this is the weight update law for neural networks, weight update law, okay. And using that, finally we saw that V dot is negative definite, V double dot is this quantity, and since R and W tilde are bounded, V double dot is also bounded by Verwald's lemma. V dot tends to 0 as t tends to 0, hence R vanishes with time. As R vanishes with time, so also the error and the derivative of error. So, if we now do the simulation taking a neural network based adaptive controller, where the neural network represents this quantity w hat phi, this quantity. Okay. Taking the single link manipulator, so we easily see that actual and desired, they are very closely following, and the velocity actual and desired also they are following, and the error, tracking error is very small in 0.00 means in 10 to the power minus 3 order. So, taking these parameters, we got these simulation results. Okay. This is the control input in the link, and this is the function approximation, this is the PD controller. So, finally, summaries in this lecture, following topics were covered: robot manipulator dynamics, various direct adaptive control schemes, computed torque control, adaptive control, robust control, neuroadaptive control, similar examples. Thank you.